Hello, guys. Welcome back to another episode of. I'm probably going to have to record this 5 times because something is going to go wrong each time. Uh, Bond enthalpies. Today's topic, and before we introduce the actual topic itself, let's go over a bit of notation that we'll probably be using. So, arrow pushing diagrams, um, basically are arrows that are used to describe where valence electrons go during a chemical reaction. Um, if we have a pair of electrons, we denote it using a curly arrow, or a full arrowhead, or for one electron, we use a fishhook or a half arrowhead. Um, there are two types of bond fission or bond breaking that differ on the electrons that were shared. So we can have a homolytic bond fission or heterolytic bond fission. Homolytic meaning um, one electron goes to each atom that was part of the bond, and um, heterolytic forms is just one pair of electrons go a pair of electrons goes to one species and you form a cation and an anion. So pictorially we can here represent this here with a single arrowhead going to each atom, whereas here we have a full arrowhead going to X and Y. We can also use these to show these arrow pushing diagrams to show bond forming. Wow. Uh, so in addition to calorimetry, Hess's law, and the formation enthalpies, uh, you can also predict enthalpy changes using bond enthalpies. Now, the thing that is now let's actually first define what bond enthalpy is. So, bond enthalpy or bond and potential energy is defined as the energy required to make one mole of covalent bonds between atoms in the gaseous phase, such that the shared electrons from such as you bond enthalpy is the bond energy required to homolytically break 1 mole of covalent bonds between two atoms in the gaseous phase. So this definition is based on homolytic bond fission, and that they produce radicals and not ions. D is the symbol for bond enthalpy, and there's your units. And that is sort of a chemical reaction to describe bond enthalpy. Uh, Bonds between different types of atoms obviously have different enthalpies. Single, doubles, and triple bonds also have different enthalpies. You're given a chart in your data booklet, and the chart is in the data booklet is shown here. Here's the chart that you'll be given in your data booklet. Uh, Know that these tabulated values are averages, and averages aren't perfect. For example, um, when you go into topic 11, you'll understand the meaning of hydrogen environment, but the chemical environment, I should say, but the type of chemical environment can greatly impact the bond enthalpy. It also only takes into account that the fact that everything is gaseous, and not everything is gaseous. So those are a few reasons why bond enthalpies aren't perfect. Nonetheless, they are useful, and there you go. They are useful. One other thing to note is that bond breaking is endothermic. You have to put in energy to break a bond, whereas bond forming is exothermic. You there's a loss of potential energy when you form a bond, and therefore you gain heat energy. You can think of it as bond forming is exothermic because it allows the electrostatic forces of attraction to interact on each other, whereas bond breaking is endothermic because you have to input energy to break those electrostatic forces that are attracted to each other. When you actually estimate these enthalpy changes of the reaction, the only thing that's different here, and I suppose this is where problems ensue, is that unlike those standard enthalpies, the formation enthalpies that we discussed literally last video, these follow the opposite formula. You go you take the sum of the bonds in the products times the number of moles of products, subtract the bonds formed in the reactant times the bonds formed in the reactant. Uh, Generally, exothermic reactions have stronger bonds in the products than they are in the reactants, and endothermic reactions have stronger bonds in the reactants than they do products. The way you can try and you can first off just remember that one's flipped and remember one of them. That's probably the way most people do it. But I suppose on a more conceptual level, the reason why it's flipped is because it's the potential energy stored in those bonds in the product minus the ones in the reactants. If you think of it as delta H is the bonds broken times the subtract the energy of the bonds formed, it makes a lot more sense because it's you break the bonds and then you form the new ones. The new ones minus the old ones is the difference in potential energy of the bond. And that's sort of how I internalize it personally, but you know, once you wrap your head around it, it's not too bad. And generally, these reactions on which the products stronger bonds, yeah, I've just discussed that. Here's a sample question. We just sort of went over some of these assumptions that the bonds are equal into the ones in the chart, and they're all in the gaseous state. Uh, gaseous state. However, those aren't bond enthalpies aren't perfect because the bond energies, as I said, just due to chemical environments, they can vary quite significantly, and it also assumes that they're in the gaseous state and don't account for intermolecular forces that may exist. Um, here's another way. Here's just bond length and strength. Again, I did this in topic 4. You can read this section if you want. The last major bit of this section is ozone depletion, in that you're expected to know how the ozone layer is depleting. Uh, Ozone naturally forms in the atmosphere through a series of reactions where O2 is broken up by UV light in the stratosphere to form these oxygen radicals, and then these radicals combine to make ozone, and this equilibrium is maintained. However, when you introduce certain chemicals, i.e., CFCs, they will, you know, they will form these radicals. They will, with UV light, they will form this radical and this radical, and these radicals actually react with the ozone to form other chlorine radicals, and these radicals cause problems because they don't absorb the same type of radiation as ozone, and therefore that's why you hear the hole in the ozone layer, and this is a big problem, and this is sort of chemically what causes it. You put in stuff that reacts with the stuff, and therefore you form stuff that shouldn't be there. Uh, you could sort of use bond length and strength to explain why um, ozone would form. Ozone absorbs different energy than diatomic oxygen. Bond order is 2 in diatomic oxygen, whereas the bond order in ozone is 1.5, and therefore the ozone has weaker bonds and therefore will take less energy to break, was compared to oxygen, diatomic oxygen. And this corresponds to different wavelengths of light, which we talked about in topic 2, does have a certain energy associated with it. You don't need to know these numbers, but it's a good, it's more for understanding. And I'm not going to go over the consequences of why the ozone layer hole is bad. I'm sure you've heard about it before. What I'm going to do, though, is I'm going to go over a sample calculation because it it makes sense to do this. So let's pick one here. So here it is. Let's do number 5. Um, when you're pause the video now, and in 3, and I'm going to go over the solution in 3, 2, 1. All right. Presumably you're back. So since they give us the structures, I'm just going to go pretty much right into it. They give us quite a bit of info. So we know that we know that delta H equals NR times dr subtract NP times dP, where D is the bond enthalpy of each. So according to the reaction here, there is, oh man, this is going to be quite a messy one here. So there are 5 of 2 N double O plus 2 N O plus 4. There's a lot of brackets here, so I apologize. So there would be 3NH plus 1NN plus 3 CH plus 1 N C C. Oh man, this is a lot. I think I covered it all. Yep. So that one bracket there is closed, that bracket there is closed, that bracket there is closed. 1, 2. I'm going to go ahead and say that that's closed. Subtract. Oh man, this is... So 12 H2O, so 12 2 HO plus 4 2 CO plus 9 N. You can substitute the numbers here on the chart. Let's do that. So bond enthalpies, we're going to have to scroll back up here to find those bond enthalpies. These things take a while, and I'm probably going to get it wrong, but regardless. So we know that the N double O is the enthalpy of, we know N double O is 587. So 587. It doesn't matter if the sign is positive or negative. You can use physical reasoning to deduce what the sign is, and then the N single O bond is, according to this thing, should be N single O. N O single is 214. The NH bond is NH bond is N times H is 391 according to the chart. NN according to this table here, NN according to the table is 158. 158. Then CH bond, the C single H bond has an enthalpy of CH414. NC, I should probably, I wish there was a, I wish I could, I wish I wasn't lazy enough to, put this into, I wish I was, not lazy enough. I wish I had enough energy to, put this into fucking Windows Movie Maker and speed it up. NC was 286. The HO bond is 463. C double O is, so C double O is 804. And lastly, N triple N is 900 something, I think. But let me check. N triple N is 945. Now let's plug this all into our calculator. plus 2. Okay. Scrolling down back to the question so I can actually see what we were working on. 214. Plus that computes. Yep, that computes. So subtract 6, 3. Plus 4 times 4 plus 9, 945. And we get a delta H of minus 3,475 kilojoules. Kilojoules for that reaction, which that does pass the does this make sense test because it's used as a space shuttle fuel. It should probably release a shit ton of energy. So, with that, guys, thank you. Sorry for the long wait. Thanks for watching, and see you again next time.